This is the third lecture from our online SEM training series. So far we have looked at the basic concepts in SEM, the uses of SEM and different types of SEM model. We'll now look at the major steps to run a confirmatory factor analysis to test our measurement models. If we do not have a good measurement model, we cannot proceed to study the entire model. So we are required to test if the data fits the model. There are 5 steps in confirmatory factor analysis. These steps include specification, identification, estimation, assessment of model fit, and respecification. Now let us look at each of these steps in detail. Model specification. This is the most important step of the 5 steps mentioned earlier. SEM is a confirmatory technique, and we are required to specify a model that delineates the relationship between variables. This we get from past research studies. The model we are testing should be based on theory. We have two types of variables: the endogenous variables and the exogenous variables. Exogenous variables can be considered similar to the independent variables in the regression analysis. These variables explain other variables in the model, and their cause is either not known or is not included in the model. The second type of variables are endogenous variables. These serve as dependent variables in the model, but they may also serve as independent variables. The second step is model identification. SEM analysis involves estimating unknown parameters. For example, the factor loadings, the path coefficient, the variance of the error terms, etc. So in SEM analysis, we are required to estimate the unknown parameters based on the known parameters. There are two requirements for model identification of any kind of SEM. We should have at least as much information as there are number of unknown parameters to be estimated, and every factor must be assigned a scale or matrix. If these assumptions are violated, the model cannot be estimated, and they are called under identifiable models. These models have more parameters to be estimated than can be estimated from the available information. It is important to note that identification is property of the model and it does not depend on the data. If a model is not identified, it remains so regardless of whatever sample size we select. A model is said to be identified if it is possible to uniquely estimate each of the unknown parameters. The third step is model estimation. Once we have a model that is identifiable, we proceed further to estimate the unknown parameters. Models that have more information than the number of unknown parameters are called over-identified models. The over-identified models have infinite number of solutions. We are required to estimate the unknown parameters using some mathematical criteria. The goal in SEM estimation is to minimize the difference between the observed and implied covariance metrics. The implied covariance metrics are those that are specified within the model, and the observed covariance matrix is the matrix determined by the observed variables. The most widely used estimation procedure in SEM is maximum likelihood estimation. Maximum likelihood estimation is full information method, that is, all the parameters are calculated at once. The estimation process begins with some initial estimates. Estimation process is an iterative process and it begins with some initial estimates. It will stop when the difference between the observed and implied covariance metrics are minimized. The next step is assessing the model fit. Often the identified models do not fit the data. Therefore, we require to assess the model fit. We have two classes of fits: the absolute fit and the relative fit. Within these two classes, we have different fits that are commonly used in SEM. The absolute fit indices are the fit indices that looks at the ability of the model to reproduce the observed covariance matrix. whereas the relative fit indices compares the theoretical model specified to a base model. This baseline model assumes no relationship between variables. Examining fit indices are very important in SEM analysis. They are useful in testing certain types of hypotheses, especially comparing alternate models. Important types of absolute fit indices. So now let's look at the important types of absolute fit indices. The chi-square value. Chi-square value looks at the hypothesis that the observed and implied covariance metrics are equal. We require the significance value to be greater than 0.05. The non-significant chi-square value indicates that there is very little difference between the observed and the implied covariance metrics. It is important to note that the chi-square value is sensitive to sample size. With large sample size, small differences between observed and implied covariance metrics becomes quite evident. Therefore, chi-square value shows good fit for small samples compared to large samples for the same covariance metrics. Thus, in addition to reporting chi-square value, it is required to look at other fit indices as well, such as the RSMEA and the GFI. The root mean squared error of approximation looks at the average size of the residual. The smaller values of RSMEA represents better fitting model, and it provides confidence intervals in significant test. Though the values less than 0.1 are acceptable, but we require values less than 0.05 to conclude that the model is a good fit. The goodness of fit index values that are greater than 0.9 are considered good fit. It is required to look at all the fit indices together rather than looking at each value independently. The second class of fit indices are the relative fit indices. As I pointed out earlier, these fit indices compares the theoretical model specified to a baseline model. These fit indices tests if the model that we have specified is better than the model where there are no relationships specified. The commonly used relative fit indices are normed fit index, incremental fit index, and comparative fit index. For all these fit indices, the values range between 0 to 1. And in general, we require values greater than 0.9 for all these fit indices. So now let's look at some rules of thumb for the SEM model fit. Often we find references about acceptable model fit. We find references for values greater than 0.9 for GFI, CFI, and NFI. However, models with overall fit indices of less than 0.9 can usually be improved. We just cannot rely on the cutoff value of the fit indices. We must also look at other information such as the pattern of standardized residuals, the beta weights, and the direction and magnitude of correlations. This information as well as the model fit indices information should be used together to determine if the model is a good fit. The last step in conducting confirmatory factor analysis is of model respecification or model modification. It is important to remember that if we have missing values, we will not be able to generate some information in software such as MOS, which are particularly useful in model specification. Therefore, we should make sure that our dataset doesn't have missing values when we are using MOS for our SEM analysis. The goal in this step is to improve the overall model fit. This steps involve changing the model to fit the data. Using modification indices, we can determine what modifications can be done to the model, such as adding a correlation between error terms or some other modifications. Modification indices gives an estimate about the improvement in the model by suggested respecification in the model. However, it is important to note that modification index are post hoc and they capitalize on chance and may not be consistent with theory. They capitalize on sampling error. Therefore, modification indices suggest changes based on empirical evidence which may not have theoretical evidence. Therefore, the general guideline to keep in mind when conducting SEM analysis is that they must be theoretically consistent and we should be able to replicate it with new data. evaluating the model. So before we conclude this lecture, let us look at some important considerations that you need to keep in mind when you are evaluating your model. First, we should use theory as a guiding principle while specifying and evaluating our model. This is particularly important when we are looking at the modification index and the fit indices. Secondly, while evaluating the model, it is important to look at residuals and implied correlations apart from the fit indices. This will help in identifying the discrepancy between the sample covariance matrix and the implied covariance matrix. Thirdly, while evaluating the path coefficient, we should look at the direction and magnitude. This should be consistent with the theory and previous literature. Lastly, it is important to look for absence of numerical problems in the dataset and the analysis results. This includes looking at the direction and magnitude of residuals and looking at the patterns of standardized residuals. So in the first three lectures, we talked about the basic concepts in SEM, the uses of SEM, different types of SEM models, and how to run a confirmatory factor analysis to test our measurement models. In the remaining lectures, we will be looking at real-time SEM problems to understand the concepts that we have learned so far in more detail. If you are looking for online SEM training or support, please contact us at admin@pytutors.com.